So guys, again, this is the beginning. Ooh, let's use the cycling term. This is the beginning of our penultimate. That means first to last. This is the beginning of our penultimate unit. And guys, this is, I got to think about this. Given the way they rewrote the test, it used to be that this is the only guarantee in free response. I'm going to leave it at that for now. I got to go back and check. There is I don't remember if they've guaranteed us a thermodynamics question, but I will tell you, this is definitely or maybe one of two guaranteed things that you're going to see on the AP test. There will be a free response question on this test out of chapter 16 and 17. This is the biggest, most complete, most important, if you will, thing that we're going to do this year, guys. It's all about acids and bases and equilibrium. So the way that this goes is today we're probably not going to get done with all the notes. This introductory day, some classes just rocket right through this. You're going to see that it's a blend of old and new. We'll slow down when we need. We'll develop some concepts as we go. If we don't get done with everything today, we'll split the homework assignment and finish on Monday, which will be totally fine. But guys, this progression goes, we're going to talk about acids and bases. Then we're going to talk about the fact that most acids are weak acids. How many strong acids are there? 7. So guys, there's 1,000 acids, right? Of those, only 7 are strong. So 1,000 minus 7 are all of the weak acids. And guys, ready for the connecting thought? What does it mean if something's weak, thinking back to chapter 5? Doesn't completely dissociate. And so if it doesn't completely dissociate, what does it do instead? Reaches equilibrium. What did you just take a test over? See how all that fits together? So guys, what we're going to do is we're going to bring everything that we know about equilibria systems, and we're going to marry that together with everything that we know about acids and bases. But then it's going to get even weirder because we're going to start talking about these really interesting systems called buffers. This will be coming in the middle of the unit, and once we get acids and bases talked about, and once we bring equilibrium into our acid-base conversation, then we're going to be doing some weird stuff where we're going to talk about these weird, trumped up, forgive me because that's got some serious baggage attached to it given our current administration. But guys, trumped up, you guys know what that means, right? Like picked up. So we're going to talk about these trumped up equilibria. This is the first year that's been a problem. No, it's not. Last year was too. These trumped up equilibria that we call buffers, and these are fascinating, especially if you're into the chemistry of biology. And then guys, at the tail end of this, we're going to talk about salts that don't dissolve all the way. Like remember we've said up until now that calcium hydroxide is a strong base? Is that kind of, maybe we should review. So guys, we've said, what are the strong bases? The hydroxide salts of what metals? Group 1 and heavy group 2, and we identified heavy as being below here, and so we said that calcium hydroxide is a strong base. You're going to find out that it's not completely soluble. It's what we call partly or slightly soluble. It's soluble enough that we still think of it as being strong, but we're going to start to talk about salts that don't completely dissolve in water. And you know, in chapter 5, when we said right now, guys, either a salt dissolves or it doesn't, we're going to talk about the gray area in between. So guys, I think you're going to find this unit interesting. I think you'll find it challenging for various reasons, and it's big. This unit is long. It's going to take us probably all the way through February. So, we ready to dig into this? You guys ready to go? So guys, what you're going to see is that a lot of this is review from what you learned last year. But as you know, when we review, we also talk about things at a little deeper level. So as we do, let's start with definitions. So guys, from last year, you probably remember that acids and bases have some tight definitions, but there are multiple definitions. Do you remember the definitions from having just looked at chapter 16? So we got Bronsted-Lowry, and we've got Lewis. And by the way, guys, with Lewis, we are only going to talk about that in passing. We are not going to do a lot with Lewis acids and bases. Frankly, the reason is because the Lewis definition of acids and bases doesn't become really important until you get into OChem your sophomore year in college. And so you won't see a lot of Lewis. You might see a multiple choice question on it on the AP test. So we're not going to dwell on Lewis at all. We'll quickly define it, not today. But guys, we've got Bronsted-Lowry, and then what's the other of the three? Arrhenius, and that's where we're going to start. So guys, we talk about the Arrhenius definition of acids and bases first because Arrhenius thought about this first. And not surprisingly, as he thought about this first, he also thought about acids and bases in the simplest terms because this was groundbreaking at the moment. So when this guy Arrhenius started to think about what makes things acidic and basic, he started to define what these things might be. And this is what he concluded. He said that acids are substances that increase the hydrogen ion concentration when they're dissolved in water. And then similarly, but you'll find out later, kind of paradoxically, if I can say that, he said that bases are substances that increase the hydroxide ion concentration in water. And guys, frankly, this is not a bad definition. What do acids do? Make hydrogen ion go up. What do bases do? Make hydroxide ion go up. And that's pretty much the case. The problem with the Arrhenius definition is it's too narrow, because in the Arrhenius way of thinking about acids, hold on a second, guys. I need my board, and it doesn't. Why would that not be working? Hold on. It didn't identify. Just a moment. Let's see if restarting it works. Go green, baby. Okay, so guys, in the Arrhenius way of thinking about this, all right, we're going green. Acids needed to necessarily contain hydrogen ions, and bases needed to necessarily contain hydroxide ions. And given the things that Arrhenius was studying, that worked out just fine. He knew about the strong acids, HCl, HI, HBr, HNO3, H2SO4, they all contained hydrogen. And then he knew about the strong bases, LiOH, NaOH, all of the strong, and so it worked. But then Arrhenius ran into something like this, and he had a problem. Because guys, NH3, ammonia, is a base, but it doesn't contain OH. So understand, this is where Bronsted-Lowry had to kick in. Because as Arrhenius was studying bases, he understood that bases increase the concentration of OH, but in the Arrhenius way of thinking, that was because they contained OH. And when they dissolved, they just gave it away. The problem is that as Arrhenius got into this study, he was starting to see examples of substances that were increasing the concentration of OH, but didn't contain OH. Does that make sense? Do you see what we're saying? So guys, this is where Bronsted-Lowry picked up. So this is the transitional thought. So in the Arrhenius definition, acids contain hydrogen, give them away. Bases contain OH, give them away. Therefore, hydrogen and hydroxide go up as they do that. But as he got into this deeper, he found out, wait a second, there are substances that act as bases that do increase OH, but they don't contain OH. How could that be? Well, guys, that's where Bronsted-Lowry kicked in. Because and you don't need to write that down, while these definitions were good, they were too limiting. And the way that they were too limiting is they didn't account for substances that didn't contain hydrogen or didn't contain OH. That's where our good friends Bronsted and Lowry come in. So guys, in the Bronsted-Lowry definition of acids and bases, and you probably remember this, what does an acid do as far as Bronsted and Lowry are concerned? They give away protons, hydrogen ions. So guys, do we need to make that connection? Because some of you are saying hydrogen ions, some of you are saying protons, and I'm not correcting either one of you. So who's right? Because they're the same thing. Do we need to flesh that out? Is that okay? Okay, so guys, hydrogen ions and protons are the same thing. But guys, and you may even want to write this in your notes with me if it helps. Guys, understand that that lines up with this, right? The Bronsted-Lowry and Arrhenius definitions of acids are functionally saying the same thing. Bronsted-Lowry are saying give away protons, hydrogen ions. Arrhenius is saying that goes up. So those are the same. So where's the discrepancy? Well, guys, the answer is with bases. To Bronsted-Lowry, to Bronsted-Lowry, a base takes in protons. But guys, interestingly, these line up as well. And let's talk about how. This you definitely want to write down. So guys, consider, for example, NH3. NH3 had Arrhenius baffled. He put NH3 in water, hydroxide ion concentration went up. But guys, NH3 doesn't contain hydroxide. What's going on? How can NH3 make the hydroxide ion concentration of water go up if it ain't got any? Exactly. Guys, do this with me. Water, right? And let's just say this right now. All of the chemistry that we are going to do in this unit will be aqueous. That actually makes things a little harder. We'll talk in a minute. But guys, as a blanket statement for acid and base chemistry, we will always understand acids and bases. Just a second, Brandon. We'll always understand acids and bases in the context of water. Now guys, why does that make things harder? Well, let's do this. This is water, right? Don't write this down. But if we look at the Lewis dot structure of water, water actually looks like this, right? Now let me change colors. What does this make water, Bronsted-Lowry? An acid. That's a proton, right? What does this make, even Arrhenius. What does this make water, given the Arrhenius definition? An acid. What does the OH make water? Give it a base. So guys, which one is it? Is water an acid or is water a base? Yes. And guys, this is one of the things that you're going to wrestle with in this unit. All of the acid-base chemistry that we're going to do is in water. And the analogy that I use is this. When you were in elementary school, you played on a playground, right? But did the playground ever get involved in your games? It's weird, right? But guys, in your world, a playground is just a surface upon which you can play. You can interact, you can react, you can do chemistry. Well, guys, the problem is that when we're talking about acid-base chemistry, water becomes the playground. You see what I'm saying? We said that acid-base chemistry will always happen in water. So you're going to take acids and you're going to take bases and you're going to have them play together. But the playground is going to be in water. And guess what? Now the playground gets involved in the games. Because you just used to think of water as sort of a context in which chemistry took place. Well, the problem is that water is not just the context, it can also be a reactant. Because water is an acid and it is a base. So when we're studying acid-base chemistry, one of the things that you're initially going to find challenging is figuring out how to deal with the playground. Figuring out how to deal with the water. Now the thing that's cool is you're going to become good at this. You are going to be empowered, literally, you are going to be empowered to choose when does it make sense to bring water into the conversation and when can we exclude the water because it's not important to what we're talking about. But it does make it different. So when we think of NH3 as a base, and guys come back to the original thought, NH3 is a base. Arrhenius couldn't explain why, but Bronsted-Lowry can. But guys, what does that mean that this base does? Well, it increases hydroxide ion. Again, you're writing this down with me, right? What do bases do? Well, they increase hydroxide ion concentration. But Isabel explained to us how. Guys, how on earth can how on earth can NH3 make this? How does it happen, Isabel? Exactly. It takes a proton from the water. And when NH3 takes a proton from water, it turns into NH4. And as it, well, NH4 plus ammonium, and as it turns into NH4 plus, this proton grabs onto the NH3, and what we're left with is hydroxide, which is a base, which is exactly what Arrhenius told us. So guys, this is why this can get a little complicated. Because when we're talking about how NH3 can be a base, the water is no longer just something the NH3 is dissolved into. The water, the setting, the context, the playground is actually critical to understanding how NH3 can be a base, because without the water, NH3 ain't a base. So what questions do you have about these ideas? Here's where we are right now. We've got different ways of understanding acids and bases. We've got the Arrhenius definition, which simply says acids, hydrogen up, bases, hydroxide up. And while that's good, it's too limiting because that can't help us understand things like how is NH3 a base? That's where the Bronsted-Lowry definition comes in. And now, given the Bronsted-Lowry definition and the fact that all of this chemistry is happening in water, now we can better understand how some things which seemingly shouldn't be acids and bases are acids and bases because of the way they interact with water. Do you feel like we just started to get into something that's about to get really real? Okay, so guys, let's do questions. Go ahead. Well, but water is, or blood is what, 80 or 90% water. Yeah, so there's, and what are we, 80% water? There's very little chemistry that goes on inside of our body that's not dissolved in water. We're basically a big bag of water. We're one big aqueous reaction walking around. So certainly, and it's interesting, we're going to talk about this later. Can I plant a seed with you? Why, when you exercise, do you breathe more? Why does your respiration rate go up? Well, yeah, you got to get rid of the seed. You ready for the interesting answer, just to set the stage for what we're going to talk about later in the unit? So guys, as you are exercising aerobically, your body produces more carbon dioxide. That carbon dioxide dissolves into your blood, forming carbonic acid, which causes the pH of your blood to drop. As that happens, there's a little pH meter at the bottom of your brain stem that dangles in an artery, and it actually measures the pH of your blood. As the pH of your blood drops, your body knows that more carbon dioxide is building up in your blood, and that's dangerous. It's called acidosis. It'll kill you. And so your body's response to that is to make you breathe faster to get rid of the carbon dioxide. And this entire system is buffered by a really interesting buffering system that we're going to talk about later. So all of this has really interesting consequences relative to biology, and we'll get into those later. Let's keep going, ladies. Yeah. No, because let's take a look at this. Here's a simple example of no. This is methanol. Methanol is not an acid or a base. It's an alcohol. So let's do this, Kami, because this is, did you guys understand Kami's question? Is anything that contains an OH, an H or an OH, an acid or a base? And the answer is no. But this is actually, we're going to spend an entire day on this. So you ready? So this is methanol. So what if methanol broke here? What would it be? Well, it would be an acid because it would release hydrogen. Does that make sense? What if methanol were to break here? Then it would be a base. But methanol doesn't do either one of those things. When methanol dissolves in water, where does it break? No. It doesn't. And that's what makes it an alcohol. So acids break to release hydrogen. Bases break to release OH. Things like this, which are non-electrolytes, drawing on the term we used in chapter 5. Things like this, which are and guys, remember what that means. Do non-electrolytes dissolve in water? Yes. What do they not do? Dissociate in water. They don't ionize. Something like methanol, which is a non-electrolyte, does dissolve but doesn't break down. The question is why? And we're going to spend an entire day and talk about this. The quick answer is, where do things break? Well, they break at their weakest link, right? So acid's weakest link is there. Base's weakest link is there. And in something like a non-electrolyte, all of the links are so strong that water can't break them apart. So what is it about their structures that cause in some molecules that to be the weak link, in others that to be the weak link? And we're going to spend a whole day and talk about why these things are true. And we're going to relate it all back to structure. Yeah, it's a fascinating day. Go ahead, Brent.
Yeah, so you said all the ones are studied in water, right?
Mm-hmm.
So in all the tests for explaining
Yep.
this kind of thing would be useful for definitions because it doesn't work in water, right?
Yeah, so you're gonna your question is good. Forgive me, I'm just gonna be honest. Your question is good, but it's so low level, it's about to become unimportant. It's not like when we get into this in a couple days, you're gonna be going, based upon the Arrhenius definition, I'm going to do, it doesn't matter. You're just going to do it, and you'll never be asked for why. But I understand it's important to you now, and conceptually it provides your framework, right? And so the answer is yes, both of these are fair game. But what you're going to find is that because all the chemistry we're going to be doing will be doing in water, they do start to blur. But what you will find helpful down the road is that the Arrhenius definition for acids and bases is especially helpful. And guys, think about this. This isn't trivial. The Arrhenius definition for acids and bases is especially useful with strong acids and bases. Why would that be true? That's true, but why else? What do all strong acids contain? HCl, HI, HBr, HClO3, HClO4. They all contain hydrogen. What do all the strong bases contain? OH, right? So the Arrhenius definition becomes especially functional when we talk about strong acids and bases, and then the Bronsted-Lowry definition becomes especially useful when we talk about weak acids and bases. Is that okay? Go ahead.
So I'm just this might be off a little bit, but when HCl associates in water with the hydrogen, with the hydrogen ions, like form like fluid hydronium.
No, and that's what we're going to talk about. Where do those hydrogens go? And we're going to look at that in just, you already know the answer. It goes to hydronium, right? But there is an equilibrium that's there. I'm realizing we're not going to get to that today. We'll have to talk about it Monday. There is an equilibrium that we need to talk about, but it's not the equilibrium you're thinking of. Yeah, it's interesting though. You're going to like it. Go ahead, Austin.
So I think my question is
To Kami's? Okay.
so when you do dissolve the NH3 and H2O,
Yes.
does it take that extra hydrogen because the factors in the NH4 and H2O comes covered with the oxygen?
Yeah, yeah, exactly. Yeah, yes, wow, good on you. So that's exactly what's going on. Because if we draw the Lewis dot structure for this, good heavens, we've got this, right? And it turns out that this hydrogen is actually more attracted to that than it is to that, and that's why they stick. Yeah, that's exactly what's going on. That's cool that you picked up on that. That's exactly. You okay? But it doesn't make sense, right? We're not going to get too deeply into it. But oxygen is more electronegative than nitrogen. Right? So why wouldn't the oxygen, this isn't, let's do this quickly, but let's talk. But I mean, as you think about it, you're like, wait, oxygen is more electronegative than nitrogen, so why is the hydrogen more attracted to the nitrogen than it is to the oxygen? Was that sort of, I saw you hesitating. Is that why you were hesitating?
I'm just trying to figure out, yeah, why it would be, why? Because if oxygen is more electronegative, why would it?
Yeah, and here's the answer. Guys, track with it. Do you understand the maybe the conflict? Here's the answer. This proton is not attracted to the oxygen. It's also not attracted to the nitrogen. It's attracted to the oxygen's electrons, and it's attracted to the nitrogen's electrons. And nitrogen is more giving with its electrons because it's less electronegative. So because nitrogen is less electronegative, it actually makes these electrons more attractive to that proton because they're further away from the nucleus of the nitrogen, meaning you get less nucleus-nucleus repulsion. So it's actually counterintuitive that the proton is more attracted to nitrogen's electrons because nitrogen is less electronegative and those electrons are a little further away from its nucleus. What we just did is why we're not talking about Lewis acids and bases, because everything that we just talked about has to do with concepts called electrophiles and nucleophiles. Things that love electrons, things that love protons, the nucleus. And those are the concepts you have to bring into the conversation when you're talking about Lewis acids and bases, and we're not going to go there. But your thinking is exactly right. This hydrogen is more attracted to the nitrogen than it is to the oxygen, and that's why it moves. The reason is because nitrogen is less electronegative and therefore more giving with its electrons, and the proton likes that, but that's where we're going to leave it. So, yeah, go ahead, Kimmy. Absolutely. So, and we're going to get into this. The term for that is amphoteric. Amphoteric means can do either. And a wonderful example is actually this. I forget the name of this ion, but this ion can actually do both. If this ion is that yeah. So this ion can do both. If it takes in a hydrogen, and these are both equilibrium processes, but if it takes in a hydrogen, it forms that. If it releases a hydrogen, it does that. And it can do both. It might be phosphorus. No, I don't know what it's called. But anyway, yes, there are other things that are amphoteric. The thing that makes a substance amphoteric is that it has hydrogens to give, making it an acid, but it also has a place to take in hydrogens, making it a base. Is that okay? Okay, so understand that when we talk about water, and you guys notice how we're just letting all these questions flow? That's what I wanted to have happen this morning. Really, I just set this is always the way we do this first day. Understand, so much of the questions that you're asking are going to be content in coming days, but I love that we can talk about these now and build some scaffolding upon which we can really flesh out these concepts later. So this is wonderful. So Kami, to your question, understand that when we talk about water being amphoteric, we can understand water as amphoteric in an Arrhenius sense. Okay, meaning it contains H and OH. So Arrhenius is that really tight, restricted definition that says gives away H, gives away OH, okay? And so in that sense, water is amphoteric in that simplest definition because it's got H and it's got OH. And that's the only substance that does because it's H and OH. Understand that this ion can also be amphoteric, but now that can only be understood in the Bronsted-Lowry sense because it's taking in and giving away protons. It doesn't contain the OH that would make it a base in the Arrhenius sense. So here it is functioning as an Arrhenius acid because it's giving away hydrogens, but this is not it functioning as an Arrhenius base because it's not giving away OH. Is that okay? Josh, are you just scratching? Or do you have a question? Are you good? Go ahead, Dan.
So, kind of getting to what Austin said, well, like what Austin was asking.
Mm-hmm.
It just makes me think, like, so if hydrogen is more attracted to nitrogen because it's less electronegative,
Mm-hmm.
then I don't know, I would think that things like that are more electronegative, like diatomic, like chlorine molecule,
Mm-hmm.
would be like super strong because it's like
No, I totally understand what you're saying, which is why we need to have the conversation that Kami got us thinking about a couple minutes ago, because what you're going to find out is that, I mean, let's just follow the trend, right? So HI is a strong acid. HBr is a strong acid. HCl is a strong acid. HF is a weak acid, which doesn't make sense because fluorine is the most electronegative element on the periodic table. Following the trend, this should be more acidic and not less acidic. Why is that? And we're going to spend a whole day on that. And I don't want to get into the reasons. You'll find them interesting, but no, you're thinking exactly right. You're just not thinking about all the factors that come into play, and we'll get there. We okay? Yeah? Okay, so guys, I love that you guys are chewing on this stuff, and that's exactly what you should be doing. So let's keep chewing, but let's chew on something different. So guys, let's now talk about this magic thing called the hydronium ion. So doesn't matter for acids if you think Bronsted-Lowry or Arrhenius definition. Guys, when acids ionize in water, hydrogen ions, protons, are given away. But guys, understand, well, let me let you write this down, and then we need to draw an important distinction. Realizing that this would be a wonderful opportunity to watch the dissolving video. We're going on number 12. Should we squeeze it in? Actually, it might be interesting. I'm gonna. You guys could narrate it, right? Okay, so let me freeze this. Okay, so let's do that. Let's go here. Let's go here, and here, and here, and here. Okay. This will be interesting. I've never tried it this way. So, guys, this is actually the easiest way I could grab this video is to throw it into the context of something I'm teaching my Gen Chem kids. So here we go. Salt dissolving in water, right?
Ionic substance such as sodium chloride is placed in water.
Okay. Here we go.
Water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution.
Okay, now let's talk. Let's be clear. What are we watching dissolve? And thank you. NaCl.
Notice that water molecules...
Okay, let's stop there. So this, I've never done this before. This is good. This is going to turn out great. So, guys, what are the forces that are attracting those water molecules to those ions? Intermolecular forces. Now, guys, I'm going to have to zoom out for this to work because I've got to draw. So let me grab my drawing tools. I'm going to use blue. Okay, so guys, this is our chloride, right? So this is Cl. What's that? Sodium. Not anymore. Because this is now HCl dissolving in water. Understand the difference would be HCl is molecular, so it would be a gas rather than a solid salt. But they both dissolve in water. So what's the difference? Well, guys, this doesn't change. When we put HCl in water, the Cl still forms this hydrated, using the right word, these hydrated ions. Guys, the thing that changes is this. That covalently bonds. When acids, strong or weak, but this is strong, when acids dissolve in water, the hydrogen, I'm being careful because let's not worry about the negative ion, but for this case it's just still intermolecular forces. But guys, focus on the hydrogens. The difference is the hydrogens that are given away into solution are not merely dissolved by the water, they react with the water. Remember how we talked about this idea that the playground gets involved in the game? Guys, when we're dissolving salt in water, the water's the playground. The salt just spreads out on the playground. But guys, when we dissolve strong acids in water, the playground plays with the kids. Literally, the hydrogen ions that are given away bond to the water. This is not a physical change. This is a chemical change. So when we put strong acids or any acids in water, the hydrogens that are given away bond to the water. They don't just intermolecular force, they bond to the water. And when they do, not surprisingly, we represent that completely differently. We do it like this. Uh-oh. Where did that? Oh, I closed it. We're okay. So I got to do, what is going on? Don't do that. Whoa! Wait for it. So guys, how do we then represent that? Well, we represent it like this. So here's how this goes. There's our hydrogen ion. Scratch it down with me. And guys, when we put this acid into water, that hydrogen ion goes into the water. But this attraction between the hydrogen ion and the water is so great that it's not just a hydrogen force, which would explain dissolving. It actually bonds covalently and it forms the hydronium ion. Now guys, let's remind ourselves about these hydronium ions. We talked about this last year. So guys, hydronium ions, these H3O ions, give acids their characteristic properties. So if you put a piece of metal in an acid and you watch it corrode, that's the hydronium ion attacking the metal. If you put acid on your arm and you're dumb enough to leave it there until it starts to hurt, that's the hydronium ion eating at your skin. So guys, when we talk about the strengths of acids, what we're actually talking about is the concentration of the hydronium ion. So we can represent this in one of two ways. Remember how I told you that during this year, during this unit, you'll be empowered to decide how to deal with water? that kind of coming back to you? This is an example of what I was talking about. So guys, ready? You're all caught up with me? What do acids do, and what do acids do? Bronsted-Lowry, Arrhenius, doesn't matter. What do acids do? Circle it. So that's one way we can describe acids, because acids give away hydrogen ions. But now answer this. When do acids give away hydrogens? When they're where? In water, right? Think through this with me. Acids always give away hydrogens. Yes. When do acids always give away hydrogens? When they're in water. Guys, the water is not a negotiable. The water has to be there in order for a substance to act as an acid. So if the water is always understood to be there, we can choose strategically to talk about it or not. It's always understood to be there. Sometimes representing the chemistry is best done without including the water. Even though it's there, we just don't talk about it, and then we'll represent acids as hydrogen ion sources. But sometimes we have to include the water because it's necessary to understand the chemistry. So now if we bring the water into the picture, we understand these hydrogen ions are not just floating around in solution, they're bonded to the water and tied up as hydronium ion. So guys, the bottom line is this. Sometimes we will represent acids as hydrogen ion sources. I see it, just a minute. Other times we will represent acids as hydronium ion sources. But guys, here's the thing. These are used interchangeably. But don't confuse interchangeable with haphazard. It's not just willy-nilly, hey, I don't want to write as much, so I'm just going to put H instead of H3O. We can use them interchangeably, but we will use them strategically depending upon context, because if we don't care about the water, we'll just say hydrogen. If we do care about the water, then we'll say hydronium ion. But understand, if we choose to just say hydrogen, in the back of our mind, we're understanding it's not just hydrogen, because that hydrogen is actually bonded to water to form hydronium. So this is what's really there. We may just not choose to represent it that way. Go ahead.
Is like every single H plus ion will eventually turn into hydrogen?
That's a good question, and the answer is for all. Did you hear Matt's question? He said, does every single hydrogen ion that's given away form hydronium ion? And the answer is yes. Understanding that anytime you draw an always or never, there's always going to be a little exception. But guys, again, Matt's question is, does all of the hydrogen that's given away bond to water and form hydronium? And functionally, our answer is going to be yes. The question is, why can we say that with certainty? And the answer is because if it didn't happen completely, the substance wouldn't be an acid at all. And I don't want to get into this too deeply, but what is the actual definition of an acid? An acid is defined as a substance that gives away hydrogens better than water can. We'll talk more about that later. Go ahead.
You said you can interchangeably use hydrogen ion or hydronium?
Yeah.
So when do you know when you want to use hydrogen versus when you don't care about
Yeah, exactly. And I can't answer that question for you yet because we haven't talked about this contextually. So guys, Brandon's question is, how do you know when to do which? And the answer is, you guys haven't been put yet in the place where you've got to make the decision. That said, let's talk about this relative to bases, because here you have NaOH. It's a base. Do we need to talk about water? No, because it's got OH. NH3. It's a base. Do we need to talk about water? Yeah, because it can only be understood as a base in water. This is an example of when we've got to include the water in our base conversations. Similar logic will inform your acid conversations. We're just not there yet. So, go ahead.
So, if the proton is bonding with the water, is covalently bonding with the water,
Which it is.
how does it do that if it doesn't have an electron?
That's a good question. And I'm really actually glad you asked. So guys, the question is, how is it that this proton is bonding covalently with oxygen? Because up until now, we've already said that covalent bonds are sharing bonds, where each one of these atoms brings an electron, and magically in this beautiful little world we live in, sharing creates attraction. Right? And we've talked about the region of increased electron density and so on and so on. But guys, when we've talked about that region of increased electron density, it's always been, forgive me, no pun here, it's always been based on the idea that each atom is bringing one electron. Well, it turns out that we can have a region of increased electron density that is not created by each atom bringing one electron, but this atom bringing both electrons. There's a different name for it. It's actually what's called, I always tongue-tie this, it's called a coordinate covalent bond. It's a subset of covalent bonding, kind of like we've got polar and nonpolar covalent. It's another form, if you will, of covalent bond called a coordinate covalent bond. And a coordinate covalent bond is defined as a covalent bond that is not created by sharing, but one of the atoms brings both of the electrons. Yeah.
Because the hydrogen is still positive and still is attracted to the electrons.
That's why it works. Yeah. You guys good? Okay, so guys, again, this is exactly what I wanted to see happen. I suspected that it would. Frankly, in years past, I've had some classes that have just been so uninquisitive and unconnected that we got through all the material today. It was sad, frankly. But I would like to at least finish up, if you will, the review. And I know that you're going, wait, this doesn't feel like review. And at the level that you're taking it, it's not review. But superficially, hydronium ion, we talked about last year, right? Now we can talk about it at much greater depth. There's one other thing that is technically review that I'd like to touch on, and then we're going to stop for the day. And guys, that last thing, that next thing is conjugates. So again, connecting to maybe what we talked about last year, we did conjugates. Guys, last year, conjugates were an end unto themselves. You were given balanced acid-base reactions, and you were asked to identify the acid, the base, the conjugate acid, and the conjugate base. That was it. This year, the majority of the acid-base chemistry that we're going to talk about is actually the chemistry of conjugates. Conjugates are not just some end unto themselves and, oh, look, they're the products of acid-base reactions. Guess what? Those products do chemistry. Shouldn't be surprising given what you know about equilibrium. So guys, a lot of the chemistry that we're going to talk about, especially in chapter 17, is all about the chemistry of conjugates. So it would be appropriate to review. So guys, this is the way this comes together. In an acid-base reaction, we'll have an acid reacting with a base. And these form a conjugate acid and a conjugate base. And understand this is not quite an oversight, but maybe. Parenthetically, you could also write the equilibrium arrow because this works also for weak acid-base systems that reach equilibrium. That, frankly, is the majority of the context we're going to talk about this. So guys, allow me to remind you what conjugate acids and bases are. and then I'm going to drop an interesting little nugget in your laps, and then we're going to call it a day. So first of all, definitions. So functionally, guys, it goes like this. When an acid and a base react together, they create, and remember conjugate, like in Spanish and French classes, when you conjugate verbs, you create new forms of verbs. So when we talk about conjugate, what we're talking about is forming new things. So what do acids do? You know this. What do acids do? They give away hydrogens, right? So when an acid, think about this with me, when an acid gives away a hydrogen, the thing that is left is now hydrogen deficient. Think about that. When an acid gives away a hydrogen, now the hydrogen's gone. Whatever's left used to have a hydrogen. That makes this thing hydrogen deficient, right? So guess what it would like to do? Get its hydrogen back, which makes it a hydrogen acceptor, which makes it what? A base. So guys, your acid actually turns into your conjugate base. Now think about this. Where does the hydrogen go, referring to our little thing here, where does our hydrogen go when it loses its hydrogen? Or I'm sorry, yeah, where does the hydrogen go when the acid loses a hydrogen? Well, it goes to the base, right? Well, we're not including the water right now. So where does the hydrogen go? And actually our base could be water, but where does the hydrogen go? Well, it goes to the base. If there's nothing else present, it could go to water. But if there's a base present, it'll actually go to the base rather than to the water. We'll talk more about that later. But the hydrogen goes to the base. So now whatever this base was, this base now has an extra hydrogen it didn't have before. So guess what that allows it to do? Give it back away, which makes it what? An acid. So the base becomes the conjugate acid. Does that reasoning make sense? If that reasoning makes sense, then I would propose to you that writing this down is a waste of your time. Because, guys, what we've got is the conjugate acid is the particle that's formed when the base loses a proton. So remember the idea, or accepts a proton. So the base takes in a proton. Now it's got an extra proton that it could give away, making it the conjugate acid. And then the conjugate base is formed when the acid loses a proton. When the acid loses the proton, now it's proton deficient, and it could take it in, making it a base. Does that make sense? Is that okay? Okay, so now guys, we've got one more thing to talk about. This is interesting. Don't write this down, just think about this with me. Let's make our base water. And now let's do this. We're going to do this twice. Let's do this once with HCl. And then let's do this again with acetic acid. You know what? Yeah, we'll come back to this to start Monday, but let's do this together now. So guys, let's talk about our products. What's the HCl going to do as a strong acid? Give away hydrogen. Where does it go? To the water. So what's going to be left over? Well, what are our products? Well, we're going to get H3O plus, and we're going to get chloride minus. Is that okay? Okay, now let's do this. This is acetic acid or vinegar. You're going to get so sick of talking about vinegar in chapter 17, you'll never eat another salad again in your life. But guys, what does acetic acid do? It's an acid. What does it do? Gives away a hydrogen. And guys, it actually gives away that hydrogen. That's called the acidic hydrogen. We'll talk more later. What's that going to form? Well, it's going to form hydronium ion and then CH3 COO minus. Now let's talk about some really interesting chemistry. HCl, acid or base? Acid. I'm just going to put A. What does that then make water? The base. Now, what does that make H3O? Is it the conjugate acid or the conjugate base? It's the conjugate acid because it has an extra hydrogen. Water plus the hydrogen makes the conjugate acid, and that makes this then, oops, I did that wrong, sorry. That makes this then the conjugate base. Does that make sense? Okay, now let's look at this. Vinegar, acid or base? Gave away the hydrogen, right? If you're not sure, compare your products. Here we've got CH3COOH. Here we've got CH3COO minus. So the idea is that this lost a hydrogen, and we know because we can see in your products that minus a hydrogen. So this is our acid and this is our base. So what does that make hydronium ion? Conjugate acid. What does that make acetate ion? Conjugate base. Are you okay with that? Now we need to talk. Switching to green just because I want it to look different. Because we've got two very similar reactions, right? We've got acids, we've got water, we've got the same conjugate acid, and then we've got conjugate bases which differ based upon what our acids were. You okay with the idea? Now we need to talk about what Daniel pointed out. Guys, the second reaction is written improperly. Why?
Because it doesn't completely.
It should be it is an equilibrium process. Why? How do we fundamentally know? Well, we know because HCl is one of the 7 strong acids that we memorized. What does it mean to be strong? It means completely breaks apart. Now, if acetic acid is not one of the 7 strong acids, by the process of deduction, what does it have to be? We're going to stay. What does it have to be? It's got to be a weak acid. But guys, here's the question. Why? Fundamentally, this is fascinating. Why is it that this is a strong acid and this is a weak acid? I ask it rhetorically because you don't know the answer. Guys, why? But do you understand the fascinating question? We've never talked about this. Why is it that HCl is a strong acid and why is it that HCl is a strong acid and acetic acid is a weak acid? You ready for the interesting answer? It's because of this and this. Here's the deal, guys. Chloride is a conjugate base. But guess what? Chloride is a worthless conjugate base. It has absolutely no ability to be a base. And because, follow the logic, because this is a worthless base, it has no ability to pull a hydrogen off of the hydronium ion, and consequently, this doesn't go backwards. It doesn't reach equilibrium, making HCl a strong acid. So you ready for that in a nutshell? Why is HCl a strong acid? Because chloride ion is a worthless base. Does that logic make sense? Now compare it to this. Why is acetic acid a weak acid? Well, guys, the reason is because this is actually a fairly good base. Acetate ion does have the ability to pull hydrogen off of hydronium, driving the reaction in the reverse direction and causing this to reach equilibrium. So guys, the idea is this. What is it that determines whether an acid is strong or weak? And the answer is the chemistry of its conjugate. If its conjugate is a worthless base, it will be a strong acid. And there's only 7 of those. For all the rest of them, the conjugates that they form actually can't function as bases, driving the reaction in the reverse direction and causing those acids to be weak. Does that make sense? Isn't that interesting? Because guess what we're going to do later on in this unit? We're going to talk all about the chemistry of the conjugates and what these conjugates do in water. Guys, it's an interesting study. So one more thought and we're going to go take a break. Please do not ever use the word worthless on the AP test. We live in such a tight, politically correct environment that if you wrote Conjugate base is worthless. Exactly. Got a lawyer. Guys, the word is negligible. Is that however you spell negligible? That's the word that chemists use. We don't talk about things being worthless because we could hurt chloride's feelings. We talk of it as being a negligible base. You get the idea? Let's take a break.